So we are considering how the flicker noise in an inverter is going to appear as phase noise at the output. Okay, so let's consider an inverter. I am simply going to assume flicker noise for one of the transistors. You can repeat the same operation for the other transistor as well. Okay. So you have some Vn. I am going to show the signs as plus and minus just for certain transformations I am about to do, but we all understand that the signs of the noise doesn't matter because anyways we are going to deal with the PSD, right? So let me rearrange this. So if this is input, I can simply say this is Vn and this is connected to the input. This is also input. Did I make any change to the circuit as such? Let me call this as A. Let me call this as B. So from A to B, no change has occurred at all in the circuit. Right? Now, I want to change the position of Vn and I want to put it on the source side. Assume that we can neglect channel length modulation. Can you tell me if this is possible? It is possible? So how should I put the signs now? The signs have to be reversed. So this is connected to input. Sorry? The plus minus sign matters when you're doing this transformation.
But after that,
once you recognize that this is noise and you are not worried about the polarity but only the PSD, then the signs do not matter. But till then, I want you to recognize that if it was a deterministic voltage signal, it would have mattered. Is this transformation clear to everyone? Does anything change in the output? The current through the PMOS is a function of source to gate voltage. The source to gate voltage remains the same in either of these. Right? So now I can simply connect this like this. This is input, your output. Now, given that I have added Vn closer to the supply, I can also assume that this is similar to a supply noise. So, if this is supply noise, then what would be the profile of the output phase noise? So, is it KVDD
square?
Yes. So, KVDD square times whatever was the voltage noise that you started with. And we assumed a flicker noise to begin with, which means it will have some constant by F relationship. So if you have a 1 by F noise spectrum, the output phase noise will also have a 1 by F noise spectrum. Is that clear? Okay, so now we have seen delay line, we have seen a ring oscillator. Let me draw a quick comparison between the two.
What to do is for the NMOS side, because that one becomes the ground side, right?
Right.
We cannot use KV, or will it be the same?
What do you think we should do? Let's say instead of the PMOS flicker noise, I considered the NMOS flicker noise.
The same thing will be there, but in place of KVDD square, what?
You will have to find the equivalent for.
KVDD square.
Yeah. So if you had a fluctuation in the ground, the output delay is going to get changed, right? So you find out what is that relationship. Basically, you plot delay versus the ground voltage, find out the slope of that at ground equal to 0. So that slope square into the flicker noise of the NMOS will give you the PSD. Is that clear? Is that okay? Okay, so now let's say I take a delay line and I take a ring oscillator. Now a delay line is simply a cascade of multiple buffers or inverters. Ring, I take the same delay line with odd number of inverters and I connect it like this. Now in a delay line, whatever is the input I apply here, the same input is going to pass through multiple stages, which means it's going to get some jitter added and then it will apply at the output, then it will appear at the output. Okay, this is what we call as a driven system. What about the ring oscillator? Is it a driven system? It is a self-driving system. Do you know the self-sustaining? But there is a particular term you use for it. Perpetual, okay, but no, the term I'm looking for is different. Have you heard of autonomous systems?
Yeah.
Doesn't require outside input. So this is what we call as a autonomous system. Now, whatever is the jitter that is being added by each of these inverters, right? Some amount of jitter is going to appear at the output. If I know what is the sigma square j, the power in the jitter added by one inverter, I can calculate what will be the power in the jitter at the output, right? Which means the jitter is bounded. What comments can you make about the ring oscillator? It is unbounded, right? Is that clear to everyone? So because you have now taken it in loop, even if in the first cycle you have some bounded jitter here, because the same edge is circulating again and again, eventually the jitter is going to become unbounded, right? So this has unbounded jitter. Now the nominal frequency you will observe at the output here is not going to vary a lot, because the input has provided the input has the same frequency. So because of the jitter, from one cycle to the next, you can talk about an instantaneous frequency. But if I were to observe it for a very long time, right, and if the jitter being added is zero mean, then if I were to observe it for a very long time, then the frequency of the output shouldn't change. Like average frequency has to remain the same. Is that clear to everyone? Do you see a reason why the nominal frequency here should change?
Because infinite jitter is getting added to that frequency.
Infinite jitter is not getting added, right? Bounded jitter is getting added for a delay. So the nominal frequency is going to remain the same. Can you comment about the ring oscillator? Why would the nominal frequency be same?
Though I also feel it should be same only, it should not change.
Why not?
Because if there is infinite jitter, then it
It
will
is unbounded jitter. The power, not jitter, is not unbounded, right?
Jitter is unbounded.
Jitter power should be unbounded. Jitter will be just something between this and this.
Correct.
Jitter
So,
power should be unbounded. We
so
don't know the
what will happen is, when the power that we calculated was jitter power. So you can calculate the phase noise power or the jitter power. Both of them are unbounded. Right? So if I were to observe the cycle like this, right? In the first cycle, let's say very little jitter was added. So maybe the variation you expect to see is somewhere here. In the second cycle, you expect to see more variation. Third cycle, further more variation. So as you keep going, the variation you can expect in the output is increasing. So the jitter is unbounded. Right? If you wait for long enough time,
the whole signal will get jittery. Like the edge is shifting a lot. Right?
edge will shift a lot eventually. So when I show a region like this, the edge can appear either here or somewhere in between.
So it might be possible that this edge goes before some other edge or something.
It cannot go before the next edge because it's a delay line.
Collapses with another edge, so the duty cycle is disturbed.
So for example, let's say here the edge happened at this limit, right? Now a delayed edge, an advanced edge is sort of going into the system. So which means here the edge is likely to appear before this. If there was no delay, if there was no jitter, let's say the edge would have appeared somewhere here. On top of this there is jitter. So either it can move this side or this side a little bit. So this keeps happening over and over again.
So it might be possible that, for example, in the negative part of the cycle, it collapses with the falling edge, right?
It cannot, right? So for example, let's say this edge happened here, right? Now, because this edge has still happened before the ideal edge, the falling edge is likely to happen before the ideal edge. But
Can
this,
the jitter by half the period of the cycle?
if you wait for long enough time, the RMS jitter can get close to half the period, right? But thing is, if I have a rising edge here, you can have a falling edge here only corresponding to the rising edge here. So because of that, it's not like before the rising edge, the falling edge will happen.
Okay, and
But
also
the
can just reach the
but the range where you can have the edges is now going to increase. The probability of finding, so for example, the probability of finding a rising edge here is going to be very small. But if I wait long enough, the probability of finding a rising edge here is going to be high, like that. Okay. Now, if you have a change in period because of shift in the edge, let's say the on time of the pulse changed a little as you went through the cycle like this. Now this changed on time is now going to propagate again, right? So this way it is possible for the frequency also to change, right? So you can have frequency variation in a circuit like this.
In that case, delay case, it can also be possible to on time.
Right, so you can have a variation, but then that variation is assuming that all of these are only adding random jitter. There is no systematic on-time variation happening in the system.
That same thing can apply here also. It can be systematically first positive, then negative.
Because you are injecting a fresh edge at the input every time, right? And if you assume that the nominal frequency here is constant, the input clock is very clean, right? Then all that you have are random jitter added to the output clock edges.
But here it could, I understood, here the input is not, it is also jitter.
Input is also jitter.
But after adding this additional jitter, the jitter can cancel because...
Possible, but you can also have frequency variation. Right. Is this bothering you that an oscillator is such an unreliable circuit? It has unbounded jitter.
Yeah, that's why I said it should have same long.
That's why I was fighting.
So this is bothering you, right? So how do you think we'll even rely on an oscillator like this for our designs?
PLL, that's why PLL.
Why PLL?
Hey, first that's why you are introducing PLL now.
So what we'll eventually do is put these very jittery oscillators where the frequency is also not fixed into feedback loops, right? And that will allow you to bring the jitter to bounded conditions and will also allow you to have nominal constant frequency. Okay, but that is for a different class. Right now, quickly tell me, if I have a standalone oscillator, right, and I want to still characterize its jitter, what jitter definition should I use? Does any of the jitter definitions make sense? Absolute jitter is going to blow up, right? Similarly, relative jitter is also going to blow up. Meaning just an oscillator without putting it in any negative feedback. An oscillator like this. It is standing alone, lonely. Period can also change, right? We said the... Sorry? So what will you compare it to? The cycle to cycle jitter, right? Because you don't expect to see a lot of jitter variation from one cycle to the other. So if you wanted to compare two oscillators, especially their jitter performance, and if they are standalone, then cycle to cycle jitter is one of the jitter metrics you can use. Now let's also quickly look at the effect of supply noise. On a ring oscillator. So as before, we'll have a nominal VDD plus some noise riding on it, and we can represent this noise signal's PSD as some SV of F. For a ring oscillator, the output that you typically look at is the frequency, right? Therefore, the KVDD is usually defined as a relationship between this supply noise and the frequency. So the definition for KVDD for a ring oscillator is change in supply voltage, change in the output frequency when you have a change in the supply voltage. Which is why anytime you deal with these parameters, it's important to look at the definition, right? So now can you tell me how I can represent phi n of t? How would I represent it in terms of, let's say, Vn of t?
Integral of
Integral of KVDD into Vn of t dt. So what is the transfer function?
KVDD by S.
So this becomes KVDD by S, where the input is the noise in the supply and output is the phase noise at the output. So if you were dealing with a white noise spectrum, even if I don't consider a white noise spectrum, can you directly give me the expression for PSD of the phase noise?
KVD square by 4 pi square
4 pi square
S square SVN.
So SV of f divided by f square. Okay. So if you had white noise as the PSD for the supply noise, then the output phase noise spectrum becomes 1 by f square. If the supply noise had a 1 by f profile, output phase noise will have 1 by f cube profile. Right? So this is an interesting result to keep in mind. So with this, we now sort of come to an end to the discussion on phase noise and jitter. We'll revisit some portions again in the next module, but we are now in a position to move on to the next module, which is about, any guesses? Oscillators. Phase lock loop after we have completely understood oscillators.
That would be negative feedback.
Yeah. So I'd like to do a quick experiment. So I want a volunteer who has the contact. So what has happened now? You had multiple people on the same call. So this was now a system with multiple input, multiple output. One output was getting fed as input at multiple points. You created a feedback system with multiple input and output. Was it stable? Right? It was unstable and you could sort of hear a ringing. Right? So this gives us the idea that I could take any feedback system, make it intentionally unstable, and I could get oscillations. Right? Now I'm sure some of you have designed multi-stage op-amps in feedback, and unintentionally you have made oscillations. Right? Have you seen oscillations in op-amp designs? Right? Yeah. So now we are a little crazy. We are going to intentionally make things unstable and see if we can get oscillations. So let me start with a very basic feedback loop. Quickly give me the expression for the output. H of s by 1 plus h of s into x of s. Right? Let's say I want self-sustaining oscillation at omega naught. Right? Which means I need to see some finite output at y of omega naught. This will correspond to h of omega naught by 1 plus h of, so let me also put in the j, h of j omega naught into x of j omega naught. But we want it to be an oscillator, meaning what is the input that we are feeding in?
Magnitude of that is -1.
So I'm asking about what input we should feed in. Nothing, right? Which means our input is 0. Right? But we want a finite output. So what comment can you make about the value of the transfer function?
Infinite.
It has to be infinite, right? So you want the value of h of j omega naught by 1 plus h of j omega naught to be infinite, right? Because you want to see some output even when zero input is being given. So that gives you the condition that 1 plus h of j omega naught should be equal to 0. Should be equal to 0, right? If I derive the condition from this. So that means what is the h of j omega naught is equal to minus 1. I can split this constraint in terms of its magnitude and angle. So how does that look like? Magnitude of h of j omega naught should be equal to 1 and angle of h of j omega naught should be equal to plus or minus pi. Right? So this is the basic criteria that we need to look for to observe oscillations. Has anyone seen this criteria before?
We used to do this.
Barkhausen's criteria, right? So this is called as. In which course did you do this?
I did 210.
210. This is also called as the startup condition for oscillation. Professor Datta had covered it when he taught 210.
He just told that this condition should not be matched to make it stable.
This condition?
But this should not be there in the system so that the system remains stable.
You want the system to be unstable?
Not only oscillator.
Acha, for an amplifier.
We avoid this, right?
So this is called as a startup condition for oscillation. Okay. So let us now understand what this condition is doing, right? So you have, let's say I take this h of s, I feed in a sinusoid at omega naught. Can you plot the output at steady state? So this is my input, this is my output. Can you plot both input and output under steady state? So you have this h of s in a loop, right? And we were trying to make this loop unstable. And we found out what is the property of h of s at omega naught so that you get oscillations at omega naught. Now I just take only the h of s. You know what its properties are, right? Can you sketch the input and output? So let's say I had a sine wave like this and I'm drawing it in steady state. I should draw it cleaner. So under steady state, how would it look like?
Negative of it.
Minus of this, right? So the output looks like it is 180 degrees shifted, or you could say that the output is inverted, right? So you gave a sine wave input and the inverted sine wave is coming at the output under steady state. So now let us analyze what is happening once I put this in the loop. Right? If I assume that you have a steady state sine wave here, you will have the inverted sine wave here, right? And again it will be inverted and it will appear here. So this way the system is self-sustaining. Okay. So also quickly tell me, do you think the system can have 0 also as a possible state? Meaning, can it have all nodes at 0?
Yeah, even given noise is completely.
So this is also a possible solution, right? Now we don't want that to be the state in which the system is settling to. So how do you ensure that it oscillates and doesn't remain at steady state?
we first at the start of the thing we just give one sine wave and we take out the input.
So you are initializing the circuit, right? Okay. Do you have to give sine wave in particular, or can you give?
Small noise.
If you want small noise, will not be a
Sine
sine wave at the end of the
wave
day,
is
right?
positive feedback, right?
It is in
So
positive
it will be
feedback.
Building up till it reaches a supply.
Correct. So any small noise should technically do the
But
job.
that will not end up in sine wave, right?
So let's come to that, right? So almost all circuits you take will have thermal noise, right? How does the thermal noise look like?
Right.
It is white, which means it has power at all frequencies, including the oscillation frequency of interest. So provided that it has some small power around omega naught, the circuit will be able to take care of the rest and settle into an oscillation at omega naught. Is that clear?
You said that any node can go to 0 also.
So for example, if this was 0, right? How can I say that it can be 0? If I assume that this is 0, like I take h of s and I give 0 as the input, what is the output? 0, right? And if I put 0 at all the nodes, this is still a consistent solution. So it could either oscillate at omega naught or it could simply remain at 0. Both of them are possible solutions.
If it is just turned off, we are trying to turn the switch and like turn the switch to the circuit on by giving some.
Correct. When we turn on the circuit, we have to make sure that it is oscillating and doesn't settle to doesn't settle to 0. Right. So one way is that we could rely on the thermal noise.
So like it doesn't auto switch itself to off state.
Once it starts oscillating, very less chances that it will switch itself to the off state.
So how can we say that if it has started, then it will go to some state when it's all the nodes are zero?
It's not that it has started, right? If it doesn't start, that is the question, right? The other answer is just the act of turning on is like applying a sudden, just turning on the VDD, turning on the VDD is a sharp transition. And anytime you have a sharp transition at the input, you will have wideband noise in the frequency domain, right? So that will also be sufficient to trigger an oscillation. Is that clear? Now the third part is, if you don't want to rely on thermal noise and VDD switching allowing you an oscillation, then you have a startup circuit. You intentionally initialize some node in the circuit such that it will oscillate after this point, right?
Which component we are turning on specifically?
So we still don't know, we haven't taken examples of the circuit yet, right? Only once you have the implementation, this will be clear. But typically, you may have a capacitor or an inductor in the circuit, and if you initialize it, think of an LC tank, right? If you initialize the capacitor, then provided you don't have any other resistance, it should oscillate forever, right? Something like this. Yes.
If you are relying on thermal noise to generate the oscillations, wouldn't there be other frequencies other than omega naught where the system will blow up?
What would those frequencies be?
Frequency will get suppressed because another frequency that condition is not satisfied.
The Barkhausen's criteria has to be satisfied. So now if there are other frequencies where the criteria is satisfied, it's possible that the oscillator can have multiple modes where it can oscillate. What will typically happen is,
It's not how HS will be looking on the frequency.
We'll come to that in some time. But before that, so we'll come to the H of S based on the circuit implementation, right? But one quick comment I can make is, it's possible for this angle criteria to be met at multiple frequencies, right? But now it's not necessary that at all of those frequencies, the magnitude criteria is met, right? So this way, in most of the oscillators you design, it will usually have one frequency at which it can oscillate. But if both the criteria are met at two frequencies, then it depends on other conditions to which of the modes the oscillator will lock to.
Like which first it will settle there, right?
It's very likely to settle there unless it has a very strong disturbance. It doesn't have motivation response.
Okay.
And so these three solutions which you discussed, these are the thermal nodes, or
Correct.
so these are the solutions when our system is basically off and the nodes are zero.
So let's say you are turning on your system, right? I mean, chip doesn't, if it doesn't have any power, no supply is connected to it, it's basically off, right? Supply itself is not there. So you will have to provide a supply to make sure that the oscillator is oscillating, right? Let's say you provided the supply. That alone also doesn't guarantee that it will oscillate, right? Now, like I said, turning on is usually sufficient if you turn on very sharply. But even then, the time it takes to settle to an oscillation is not under your control, right? But if you initialize your circuit with a starter, because you have designed a startup circuit, which would be something like charging a capacitor, you know the capacitor value, you know the current you are providing using the startup circuit, so you know the time it is going to take to charge the capacitor. And once a capacitor is charged to something, oscillations are going to start immediately. So that way, if you want a good control over the startup time for an oscillator, having a specialized circuit for starting the oscillation is a good idea. Is it okay?
This startup circuit, it will be automatic, or will there be a really?
You can have both of these options are available, right? Some startup circuits will get triggered once VDD is on, right? For certain startup circuits, you can choose to have a reset signal for triggering it. Okay, now one interesting question. We talked about how our oscillator is supposed to be self-sustaining, right? So the question is this. Let's assume that you took your system. Let's assume that you took the system and you gave an input at sine omega naught. So in this discussion where we talked about how even without an input, all the nodes can sustain an oscillation at omega naught. Let's assume that you applied a sinusoid at omega naught at this node, at the input. What do you think will happen? How does it blow up? Can you sketch quickly and see?
It won't blow up, it will go to VDD minus VDD.
Is the question clear? So if I take this, right, provided I give the sufficient startup condition, even without an input, it is going to oscillate at omega naught. What happens if I give a signal at omega naught as the input?
It will just keep adding up.
Keep on adding.
The adding term will just be doubling up.
Like our transfer function will be now h of s upon 1 plus h of s. It will depend on its magnitude and phase.
Right.
Assume
Like starting with sin omega t, the second round it will be 2 sin omega t, then it will be 3 sin omega t, then it will go to VDD minus VDD.
It will, assuming that there is no limit of VDD, it is going to blow up. Is that clear? You can quickly, apply a sinusoid, see what is the input coming back, and what happens to the input side when you have both.
The output of the oscillator was such that it was minus of that sinusoid, so that both of them were added to zero.
Minus plus minus.
So H of S is also providing an inversion, right? Plus, because of the negative feedback, you have one more inversion. Yes. Yeah. So let's say I applied a sinusoid here, right? So we'll look at a very crude explanation for this. Right? So in the first cycle, you will have the sinusoid appearing here. This is going to get inverted. Right? Now the inverted sinusoid is again going to get inverted when it moves from this negative sign to the plus sign. Right? On top of it, you have the next sinusoid coming in. So both of them will add up and you will have double the amplitude. Now this higher amplitude is going to get inverted here. That is going to come back and will again add to the next sinusoid. So now it becomes 3 times, right? And this will keep happening, and this is eventually going to blow up like this. Is that clear? If the system is already capable of oscillating at omega naught and you apply an external omega naught, you can expect to see very, very large amplitudes. Okay.
So if you don't give a sustained input, will it not blow up still?
If you don't give a sustained input, when the signal comes back, there is nothing else that is adding from here.
Okay, just putting.
It is just,
It was happening in our WhatsApp.
yeah, something similar was happening in the WhatsApp call also. Some input went in. I think now it also depends on how much amplification somebody's speaker had, but it was a very unstable feedback system. I think that is a conclusion we can make.
We can also start by just giving a short duration of this sinusoid.
If you had the ability to generate a sinusoid for a short duration, right, why not use that source as your main source? All of this because we don't have a source at omega naught, right? Right. So now let us look at how we can analyze and see if a given circuit can act as an oscillator. There are 3 main ways in which you can do it, so I'll list them out. The first method is, of course, to rely on the Barkhausen's criteria. So you will analyze and identify 2 things in the loop, right? One is what is contributing to H of S, and the second part is what is contributing to the frequency independent negative sign. So identify both of them. So here H of S in the figure was this. You also had a minus sign which was independent of frequency. At all frequencies it is giving you a negative sign. So identify both and then you solve for H of j omega naught equal to minus 1. Now the second method is to take the closed loop system and then you force some initial condition on it and simply observe how the circuit is behaving to this initial condition and whether it is going to result in an oscillation. Right? So you force an initial condition and then observe for parameters of oscillation. We'll take an example to go through all 3 methods. Now the third method is, so in the first method we said that the input to output transfer function was becoming infinity, right? Now it's not necessary that I have to deal with input and output at separate nodes. I could talk about input and output at the same node. I inject something to this node, and if I see infinite voltage, that means that the transfer function is infinite, right? So I could inject some current at j omega naught, and then I observe whether the voltage at that node is tending to infinity. If it is tending to infinity, that means you have infinite, the transfer function is blowing up to infinity at omega naught. So this corresponds to having the impedance at that node, which is equal to V of j omega naught by I of j omega naught going to infinity. Is that okay? So the step is inject I of j omega naught at a node, and then you calculate conditions for z of j omega naught to be equal to infinity.
What would you consider infinity in the real world? You push in a current, what would you consider as infinity?
If I give a sinusoid, so I give a sinusoid, the models we are dealing with are linear models, right? Which means we are going to solve this for small signal. So in the real world, what will happen is the voltage will increase so much that it will come out of saturation where the linear model is not valid. So that will be the limit. But in the regime of linear model, the value should blow up to infinity. So now we'll take an example, solve it using 3 methods to see if the circuit is oscillating. Okay. So everybody's favorite common source amplifier. I'll consider some capacitance at the output. And because we need a feedback, I'm going to connect the output to the input. So the question is, can this oscillate? So start by method 1. Identify the negative sign, identify h of s, and see it's possible for it to meet the Barkhausen's criteria.
But also can I take 5 minutes early?
Okay. You have a class after this?
Last semester, after this one.
But can you send me a mail with the information about what class is being offered? Because I don't think it is fair to the students that classes get scheduled immediately after one class ends. I know, but these are extra classes, right?
Yeah, not extra classes. These are rescheduled classes. I was not going to take 2 classes, so.
If you took R naught, it will come parallel to RD. That's that will not affect the result. Okay, so let me quickly sketch its small signal model. The portion that is giving you minus h of s is here. Right? So this is giving you minus h of s. So which means what is the expression for h of s? So minus h of s is minus GMRD into the minus GM into the impedance, right? So this is going to be GM into, simply write it as RD parallel 1 by S here. This system has only one pole. Right? So what is the maximum phase shift that this can offer?
Minus 5 by 2. Okay, minus 5 by 2.
So this is going to be equal to minus pi by 2. So you can never meet the condition where angle of h of j omega naught is equal to minus pi. Right? This is not met. Therefore, it cannot oscillate.
Now, how to check for this frequency independent negative sign?
So if I were to write the expression will come out to be minus GM into RD parallel 1 by SCL. This negative sign is negative irrespective of the frequency of operation.
The frequency independent negative sign of what?
Frequency independent negative sign in the loop. Right? So you are working with a loop. The loop is going to have a frequency independent negative sign and some phase shift associated with the h of s. So you need to recognize both separately so that you don't equate minus of h of s, you don't take the angle of minus of h of s. That's all. Okay, now can you quickly do using method 2? So you can initialize the capacitance with a voltage. For now, you can ignore RDS to keep the calculation simple. So let me simplify this thing a little bit for you. I'm going to redraw this connection. So this connection is between the drain and gate of the transistor. Let me redraw it like this. Right? So now what can you replace this with? 1 by G, right? So now your circuit simplifies to, you have 1 by Gm, you have another RD, and then the capacitance, I think I used CL, right? Now if you initialize this capacitance to some voltage, capacitor is simply going to discharge through the parallel combination of 1 by Gm and RD. Can you have oscillations?
For oscillation, what should happen?
So you observe for it, right? Now here we see that it is discharging. If it was oscillating, you would see that whatever voltage is being dumped there, it will result in an oscillation at that moment. I'll take another example and then it will be clear. Okay, therefore no oscillation. Now apply method 3. Do you remember method 3? You basically have to find out the frequency at which any of the nodes in the circuit can have infinite impedance. So injecting the current and looking at the voltage is one way to check the impedance, but if there is an easier way out, feel free to use that.
Obviously, the resistance from that side is, we are just looking the R output, right? We can just look at the
You can
R
look at the R output also.
Technically, if you look into the gate, it's infinite.
Is it though in the circuit?
Not
So you simply have two nodes in the circuit, right? You have this node and the ground nodes. Right? So I can sketch the circuit as you have a 1 by Gm, then a resistor, and then a capacitor. What is the equivalent impedance? Parallel combination of all three. So that is going to be equal to 1 by Gm, parallel RD, parallel 1 by J omega C. Can this go to infinity at any frequency?
DC, at DC.
It is parallel combination. So even if one resistor, right? Is that clear?
Yes.
So Z of J omega cannot go to infinity. Therefore, no oscillations. So we have verified that the same circuit is not going to oscillate using three different methods.
But it can go to infinity at a particular frequency.
What frequency? So this quantity cannot go to infinity, right? So this is some finite quantity, this is some finite quantity, parallel to some infinite quantity.
R parallel 1 by C can go to infinity, like at 1 by RC.
1 by J omega C can go to infinite. So what are you saying?
Suppose there is a R in parallel with C. It is a tank circuit. Tank circuit. Like
It is not tank. LC is
suppose there is a R and C. Both are in parallel.
okay.
Equivalent resistance or equivalent impedance will be R times 1 by C by R times 1 by C.
Okay.
So R by 1 plus SRC. So it can go to infinity at S to minus 1 by R.
It can go to infinity at S equal to
Minus 1 by R.
minus 1 by RC. That is the, one quick answer I can give you is there is still a 1 by gm here, right? But even this I am not completely convinced. Because, yeah, that is not how you look at the magnitude of the transfer function, right? You have to put in s equal to j omega, and then you have to see at what omega it is going to infinity. You're following? Yeah.
When it will go to zero only at a complex.
It goes to 0 only at a complex frequency. Right.
Suppose we derive a transfer function which has that complex poles and zeros.
Right.
Then we say that s is equals to minus z1 is the zero.
Those are the 0 and pole positions, right? Maybe we can take this discussion after the class, right? Okay, so I want to give you the second circuit that you can analyze. So I start with the same common source amplifier. This is connected to ground. I connect the output to the input, just that you now have a delay in the path. Right, and this delay is, let's say, delta t. So can you use method 1 and see? I have just introduced an ideal delay, that's it. You have a common source amplifier, output is connected to input, just that there is an ideal delay when you go from the output to the input given by delta t. So you can use method 1 to analyze if the circuit can oscillate.
This is similar to adding a capacitor, right? Because it's adding delay in the circuit.
It's not exactly similar to adding a capacitor. There are some differences. This delay is now frequency independent. Any delay offered by the capacitor was frequency dependent.
Even those guys, parents are not, you are not.
So let me do the small signal model. This is connected to the ground. I'll retain the transistor image as it is. I can put the delta t here, and then this is connected like this. So now what is offering you minus h of s is this component. Right? So now can you tell me the expression for h of s? This will be GMR into e power minus s delta t. So now I can write an expression for h of j omega. So GMR is okay to you? What is the expression till here? Minus GMR, right? So minus GMR. Now the signal here will be a delayed version of the signal appearing here. So it is GMR into e power minus s delta t. So what is h of j omega naught? This will be GMR into e power minus j omega naught into delta t. What is the angle of h of j omega naught? That is minus omega naught delta t. Okay. So all that we have to check is whether this can be equal to, because I have a minus sign here, I'm going to put minus pi here. And that gives you omega naught equal to pi by delta t. What is happening in the tutorial block today? A lot of crowd outside. Some quizzes there. Yeah. So omega naught is pi by delta t. Now all that you have to check is at this frequency if it can give you a magnitude of 1. So I look at angle of h of j omega naught. What is the expression? GMR. So this has to be equal to 1. And this is not a condition that is harder to manage. You can design for it. Right? So, in effect, this given circuit can oscillate with a frequency of omega naught equal to pi by delta t. This is okay? We have a scheduled class till 6:30.
But the rooms were all available.
I am not sure how it is available. There is a scheduled class every Mondays and Wednesdays here till 6:30.
Sorry. How long will it go?
I can leave at 6:30. 6:30.
6:30.
Yeah. That is a very good point. So we will deal with it when we get to the implementation part. Right? But right now, as a model, is this clear? Now I will leave it as a homework for you to try and figure out how to apply method 2. We will directly move on to method 3. Can you quickly see if you are able to apply method 3?
I have copies over there. Copies over there. Sorry.
लेकिन यहाँ पे 6:30 का scheduled class है.
I'm carrying it. Thank you, ma'am.
Right. So apply method 3. You simply have to calculate and see if at any of the nodes the impedance can go to infinity at omega naught.
Why did you take negative sign of S?
Why did I not take negative sign? Right. So this whole block has to give you minus h of s. Right. And what is the gain of this whole block? That will be equal to minus GMR into the delay function. Therefore, h of s.
Break the loop and apply an input.
Right.
It is like H of S.
This is minus h of s according to the convention we are using. Yeah. Right. Let us consider the loop we started off with. This is okay? I break the loop here. You have a minus sign here followed by h of s.
So you are not applying input there.
I am not applying input here. We are looking at the loop. Right? And this is minus h of s. 6:30. Thank you. We'll wrap up the class.